It's Amber Alert, huh?
So they've submitted the proposal, but then
Okay, you'll need to ask. I need to start class right now, so you need to ask me a bit later. So welcome back, everyone. So I think the homeworks are not great yet. They'll be been told there's like they're partially done, but there are lots of you. They'll be done probably at some point over the weekend. The second homework has been posted. So let me just remind you that the kind of the structure of the class is there are kind of three components in the class. So there are the lectures. So these are meant to give a broad overview, kind of a to kind of explain the math behind what's going on. There are also going to be some stories, sometimes this will also include some deep dives in some areas. So some of the stuff on like the p-stable distributions, a lot of you may not need that, but some of you might find that cool. The other part, the next part is the homeworks. So these are the learning components of the class. So the homeworks, you're going to get a grade for it, but it's more kind of a hands-on and often has to do with the coding of like the basics. So I want you to kind of make sure you cover the basics, and often this will have some clean data. So I'll try and clean the data. It's easier to work with, and this will be in contrast to the project, where it's going to be like a deep application. And this data is often dirty data. So you're going to have to kind of see what it's like to work with whatever data you found on the topic. And so the homeworks, you'll see that. If you haven't seen it yet, we posted 4 text documents, and they've been processed. So if we did it correctly, they should only have 27 possible characters, just lowercase letters and spaces, right? So you don't have to do too much to clean this sort of stuff up. What?
There's a hyphen in one of them.
There's a hyphen in one of them. Okay, so you should treat the hyphen as if it wasn't there, and someone please let me know, and I will update the document. But the hyphen should be treated as if it is not existing. So sorry about that. So hopefully it's cleaner, so you don't have to deal with these sort of things. So the other thing, I'll give you a couple of hints on homework. On the homework 2, these random hash functions in order to do the min hashing, and the easiest is the easiest hash function is usually something that's one of these that's is built in to a language, and the one I talked about in the notes is like the SHA-1 hash function. This is because the ones you used for the first assignment, they were based on just numbers, and it was easier to roll your own. But for this, you'll need to be passing in strings. And so you can convert those into numbers and then use whatever you used before. But there are front ends for like SHA-1 that you can get that will take in an actual, will take in a string. So you don't have to worry about the conversion. So that's just the easiest way to do it. This second thing to note is there's these notes there's these part of the notes under the min hashing where it's called the fast min hashing, and so this is much easier to use than the kind of the full way where I explained how it worked, where you create a matrix and you permute it and do all that. So just using the fast min hashing will be easier to use. So those are kind of some places where people have gotten stuck in the past, and hopefully this will help all of you out. Okay, so that's due in 2 weeks, I think, February 18th. Yeah, so in 2 weeks. So you should have enough time to do that. Any questions on that came up? All right. Okay, and if you had tried to look at if you had been browsing around the website and had found a bunch of documents before and then didn't, and saw those in your browser and didn't, you make sure we refresh them, otherwise you might re-download the old ones. The new ones should be about like Stephen Hawking's and physics and stuff. If they're about something else, then those are the wrong documents. They're from last year. Okay. So let's see. So what we'll talk today about is approximate nearest neighbor. Okay. So, and this discussion. So, we already talked about this stuff with locality-sensitive hash functions, and these allowed us to answer kind of these two questions, and we spent more time kind of focusing on one of them. The first one was, so given a data set P, find all close points. Okay, and the other one it can handle was given P and a query Q, say find close points to Q. And so we'll more focus on this one this time. Although this techniques we'll talk about today, you can also use towards the first one, first question, but they're not always the best ways of doing that. And so the reason for doing this is LSH is kind of fairly general. It works for a very broad class of these distances and a broad class of these similarities, and we talked about a bunch of them on Monday. So the stuff we'll talk about today will be mainly where we're dealing with the Euclidean distance, and that is again where say P and Q are these vectors in RD, and then the distance between them is Q minus P2, right? So this is just a straight line distance. Okay, so this will be easy to talk about. Some of these techniques will carry over to some of these other distances as well, but this is kind of an important distance. And this is, say, finding close points, but often what you want to do is to find the closest point. So if you're given a data set P, then we'll define this quantity, and I'll use this notation, phi of P, so this is uppercase P, of a query point Q is going to be the arg min, so that's a point P in the set of the distance between P minus Q. And again, if I leave off the 2, the sub 2, usually that's as the default is the 2 norm. And it could be under a different distance. That's fine too. So I use this notation. So who has not seen this arg min notation before? So this is okay. So have you seen like a min notation? So if I just wrote kind of this part here, you would has anyone not seen that before? Just the min? Okay, so this min, I'm saying I'm taking the minimum over all values or all points P in the set. Okay, so I'm looking at every point in the set, and given some query point Q, I'm finding the one that minimizes this. And just the part in blue, this blue part is just returning the value of the minimum distance. Okay, so let me write some example here. So let's say these are my points P1, P2, P3, and this is, say, P4. So the union of these is my set P. And then I'm going to have some query point Q. And I can then think of computing the distance from Q to each of these points, right? And I take the one that's the minimum. Okay, so this distance here, this distance is the minimum value. That's min of all the points P in this expression from this set. And then the argmin is the actual point. So that the argmin would return actually this point P3. So this point is the argmin. And so that means it's the argument which minimizes this function. And so you can do a max here instead. If the set is actually not discrete, then you can use infimum, and there's some, there's some mathematical slight differences. But we can just use the min here. Okay. So we're going to be looking for, given a set of points, say P1 through P4 here, we want to quickly find, given any query point, find the point which is the closest. That's going to be our goal. Okay, and so we can do that with this. We can do that with locality-sensitive hashing. There's a way to do that, and that's what we do is we take all the points in set P, and all this, I should say that, so if the set P is small, even if it's maybe even if it's smaller than 100, because of some overhead in some of these techniques, if you're bigger than one dimension, it's often not that bad just to check every distance, just to calculate all the distances, right? But we're going to be interested in the case where the size of P, this is the number of points, is equal to something like 1 million. That's a good thing to think about. It could be larger. Even at 1,000, a lot of these things are very useful. Even at above 100, it's probably useful to use some of these in low dimensions. Okay, but think about it's 1 million, so we somehow want to pre-process these. So with LSH, what we do is we can put these into all the hash functions ahead of time, and then we have these different hash tables. Each band there's a hash table, and we check to see if there are collisions. Now we just want to find the closest, so we need to set some value of so LSH. LSH needs some threshold tau. So we'll build a structure with the threshold tau to do this. So the problem is we may not know this distance. If we set tau so it was really small, then we might not find any points. If we set this radius to be tau, we might not find any points. If we set tau to be really big, and again, that's a bad circle I've just drawn there, but pretend this is a circle. If it's really big, we're going to return everything. So this isn't helpful either. So what you can do is you can build some different levels of tau, some really close and some far, and so then you can do like a binary search on these. If it's empty, then you need to go to a larger layer, a larger value. If it's too full, then you don't want to check all these things. When you start finding a bunch of them, then you say, well, I have too many of these. I'm going to go work at one of the smaller taus and do a binary search on these to find the right one that has only a small number of things you have to check. Okay, so there's a way to do this with LSH, but this is not kind of it's not really the best, often the best way of doing this. But for some abstract distances, it's still pretty useful. There are other techniques that work much better, especially in lower dimensions. that we'll talk about for solving this nearest neighbor problem, or an approximate version of it that we'll get to in a bit. So before we talk about how these work, I want to spend a little bit of time talking about two other issues. The first is I'm going to go through an example. Actually, this will be the second thing of of way where you'd actually generate data points in 128 dimensions, where you'd actually get these 120 dimensional vectors where you want to find nearest neighbor under Euclidean distance. So this is a high enough dimensional space that you need to think of things like LSH and other of these techniques in order to work with, and it makes sense to use the Euclidean distance. But before that, I just want to say just mention some use cases. So nearest neighbor is kind of a very central kind of building block for a lot of tasks in data mining and machine learning. So in machine learning, one of the very basic classifiers is called a KNN classifier, where basically you have a data point you want to predict what it's going to be like, and you have a data set of things that you know how they're like. So you find the K closest of these, and you build your prediction off of those. Maybe you take the average, or if you're trying to guess if it's true or false, you vote based on the K closest ones. And this works very well in like a lot of settings if you've defined your distance well. So this is one setting, and you need to answer these queries very quickly. You don't want to check against everything else. So one thing, the other thing is we want to, and I've mentioned this before, we want to detect duplication. So we're Google, we're crawling the web, and we'll talk about how they do this later in the semester, and they find a new web page. They want to say, is this a copy of another web page I've seen before, or is this some new content? They kind of want to understand that, so they don't have to kind of, they don't want two things similar to each other in the search results that they're presenting. Or maybe it's two products that are very similar, and you want to kind of advertise them together. So this detecting duplication. It's also going to play a really important role in clustering, which we'll talk about starting next week. So we'll see how distance and finding the nearest neighbor is going to be very kind of something you need to do over and over again on some sort of data set. So these are just kind of some examples of very, very important tasks. One other things could be like finding coffee, right? So if you fly to a new city and you're in the middle of a new city and you want to find some Starbucks because you really need coffee because you are jet lagged or something, then you want to find the closest Starbucks, right? So that's finding the closest. You're here. These are all the Starbucks in the city. There are two across the street from each other, and this one's the closest one, right? So this comes up all over the place. All right. Okay, so let's talk about, so this kind of sets things up. So I want to talk about a way to generate, or these what are called these SIFT features, and these end up being points in RD where D is equal to 128. Okay, and so this will kind of be a discussion about how you would get these sort of data, and they come, they're used for understanding some pictures, or if we're looking at some images. And what they do is they kind of, it's part of a process that helps you identify important parts of images. And these are things that if you take two pictures of the same room from different scenes, then these will be items in the picture which you can kind of correspond to each other. Say, these are probably the same. And so it's a way of doing things. When you take pictures from two different locations, then there can be some differences in scale in kind of in the location in the picture. So this might be shift. So there's going to be differences in the rotation. So you can rotate the camera. My wife always likes to take pictures with the camera rotated 45 degrees for some reason. So you want to be able to find things even if someone kind of turned the camera a little bit. And there are also things like, so this isn't great for issues like with lighting, but there are other things where it may kind of, if there's issues in lighting that are different in the two pictures, then it's also going to have to help to kind of pull these sort of things. You want this to be invariant to these. And so this is either scale or shift invariant feature transform or something is what this stands for. And so, okay, so what you want to do is you want to take some image and somehow create a set of these points in 128 dimensions that are going to represent important parts of the image. And then once you have that, you can you're going to say, well, I give it another image. I want to find the point which is closest to this. And then I'll think, okay, those are probably the same spot. And then there are ways to kind of align pictures by aligning the two spots which are the same. So how do we create these vectors? So before we do that, we need to think, what is an actual image? All right, so let me try and draw some picture here. So an image usually is going to be some nice, rectangle or square, and then you're going to see this is, there's going to be someone in here, and then they're going to be staying next to a bike, and this is, and then there's like a tree in the background here. Okay, so this is my image, and then on top of this, so this is what you think of it, and it's now we have all these high resolution things, but really this is divided up into these pixels, right? So there's this underlying grid underneath this image here, right? So, and I won't draw all of these things here, but there's this grid, and each of these is a pixel here, and so this little piece in here is a pixel, and so typically you just store a pixel as three values if it's color, as it's going to have a red value, a green value, and a blue value, and combine these together gives you a color on that pixel. We're going to simplify things and just say that there's one value which is a gray value, and often you'll have, and if you have a black and white picture, you'll just have a gray value which will be some number between 1 and 256. 50 shades of gray, there are 256 shades of gray, as it turns out. It's even more exciting than you thought. Huh? So this image, there's a lot of stuff going on here. It represents it, but I think there are like millions, or I don't know how many pixels there are in most images now. But it's just going to be this long vector of these values, of these gray values, right? So now this picture is just going to be a vector, or G1, G2, up to G, N. I don't know how big. For each pixel, there's one of these values. Okay, and so comparing images just based on these pixels, kind of how much they align to each other, it's not at all scale, location, rotation, or this lighting invariant. They can be very different of the same objects. One pixel shift may cause if you're taking as you're moving the camera, the lineup of these pixels from one image to the other is going to be very different. So this is not our vector. What we want is to identify some important of these pixels. And so an important ones may be something like this pixel here, which is on one of the corners of the bicycle, right? Or on the edge of someone's head, or right on their neck, or at the base of a tree. Right? So basically what you want are these things which are corners. corners in image tends to be things that are going to be stable across different views. Okay, so what we're going to do is we're going to identify these corner pixels, and then we're going to, and then we don't just want to line up the gray color because that won't tell us enough. We're going to turn this pixel, represent just the important ones, into this 128-dimensional vector. Okay, and this is going to be called the SIFT feature. Okay, and okay, so I'm not going to go into all the details of how this actually works, but I'm going to give you kind of a rough idea of how you would get these 120-dimensional vectors and why they're useful, what's going on here. So how many people have taken a class have taken the class here in computer vision or the image processing class? A few of you taken that? And do they talk about SIFT features there at all? No? Okay, so SIFT features are, from what I understand, in computer vision, they're used a lot. SIFT, they're like somewhat patented. There's some copyright or something on them. There are some other variants of these called, let's see, there's another set called Surf, and there's another one called Brisk. And I think Surf may also be patented, but Brisk is open source or something. There are different ways of creating these high-dimensional vectors you can use. And these work well in a lot of these vision applications. Okay, so to kind of see what's going on, you're going to get the first thing to realize is when we look at one of these pixels, we don't want to just look at just one by itself. We want to look at its neighborhood. So let this be a pixel X that we're creating the SIFT feature for. Okay, so we're going to create SIFT feature at this value X, and maybe this is this one here. Okay, and so we're going to look at some neighborhood structure, and we'll call this N1, N2, N3, maybe N4, N5, N6, N7, N8. So you're going to have all these neighboring pixels, and then you're going to look at all these differences in pixels. So you look at like N1 minus X. And these pixels store a value, this G value, and you're going to look at this. This is an estimation of the gradient, right? So you're going to get, for each pixel X, you're going to get these 8 values. So you're going to get, well, let's call this, V1. So this is V1, V2, up to V8. Okay, so you're going to get these 8 values, which are the gradients. And so what you first want to do is kind of pick the one that's the largest. So you're going to create these 8 values, and whichever one has the largest change, let's say it's this one, then you're going to do a rotation of this, so it becomes V2, V3, V4, up to V8, V1. So you're going to, so if it was V3, then that would have been first. So you're going to, so the first one is the largest, and by doing this, you're kind of rotating this image. You're kind of doing a rotation like this, like 1 pixel over in this case, to where the biggest difference is. And this is kind of supposed to remove the rotation effect. So for each pixel, you kind of figure out the way that is changing the most. And the idea is if I'm on the side of this person's head here, it's going to change the most on this edge, or maybe on a corner, in this direction. And so this is going to kind of give you a sense of, you're saying this direction towards N2 is going to be the, this. So if I took it from a different angle, I should rotate about the same. Now I only have 8 possible angles, but this is usually enough to get the main idea, what's going on. The other thing is scale. This is looking at just 1 pixel apart. In practice, what you actually want to do is look at kind of multiple different scales of these like around the central pixel. So I showed you how to do this if I was 1 pixel apart. But really what you want to do, there are 2 ways that scale is addressed. But instead of doing this, I'm actually going to kind of, let me draw a new thing here. I'm going to put X at the center here, and I'm going to put a 4x4 grid around here. And instead of just doing this at this 1 pixel, and now this doesn't quite align with pixels, but think of this as I've chosen some scale somehow, where this is, going to be something like, maybe it's 10 pixels. And so then I'm going to, within each of these, I'm going to take like an average using some Gaussian smoothing and some way I won't get into, and create these this gradient difference at each of these 16 values here. So there are 16 different grid values that are around here. And for each of these, I'm going to create one of these red vectors. And so this 16 times 8 is going to be equal to 128. Okay, so instead of just looking at this difference in values at this 1 location centered around this pixel, I'm going to do it at 16 different locations in the neighborhood and get a sense of what's going on in the neighborhood. And then I need to choose how big this neighborhood is. I'm going to do it, this is 10. So you kind of do that by doing Gaussian smoothing of the whole image at many different resolutions. And you only do it for the pixels that have kind of a big difference in how the smoothing works at 2 different levels of smoothing you try. And there's some details on how you do that. There's a lot of details I've skipped here. But the main thing I want you to see is that you're kind of transforming this 1 pixel into this representation that has these 16 sets of 8 vectors, these 16 sets of 8 values, and you're just going to line them all up. And that's going to create a 128-dimensional vector. Okay, and you're always going to have to line them up in the same order. So this is like 1, 2, 3, up to 16. And each of these, you're going to create one of these vectors here. And so all of these values, you kind of want them to be, they're all kind of roughly on the same scale, and you want them, they're roughly the same importance somehow. When there's an interesting story about this paper. This was kind of, this may seem kind of mysterious. Why are we doing it like this? This was published by David Lowe in, I think, 2007. And this was in some journal in computer vision. He actually came up with this like 5 years earlier, but couldn't get this published. And eventually he sent it to a fairly, like a lower tier journal in computer vision. They said, sure, why not? And they published it. And this single paper has, I think, had about half the citations of the entire journal has been this one paper. It's really heavily used in doing and understanding images and so forth. And a lot of people in the community didn't understand, why are you transforming it this way? There are a lot of modeling choices into here that I didn't explain. But the really useful thing is that it transforms an image into a set of these points, which are then just high-dimensional vectors. And then we can use a lot of these techniques like LSH, which was coming out around the same time as this, and some other techniques I'll talk about soon, to kind of find these nearest neighbors and use this for defining alignment between images. So what you would do is you would take a bunch of images and you would create these SIF features for identify the important pixels and create these features and throw them into some big data set. And then you get some new image and you create the SIF features for that, and then you find the nearest neighbor of each of those. And if they're all coming from a set of images, or one image or images that overlap what they're taking pictures of, there's probably something in the image which aligns with the one that you have in the picture. And this just worked extremely well, very scalable, and this allowed a lot of these computer vision algorithms to really scale up to sizes. There was a big leap in the scale people could work at here. Before that, a lot of the stuff was identifying things within individual scenes and segmenting them, and this was integral in allowing them to scale up a lot of these techniques. And now there are these new techniques based on deep learning, and they're not necessarily using SIF features, but they're using things that kind of look like SIF features. They're using a certain type of wavelet over these images, which is kind of figuring out the rotation in a different way. It's kind of like a squished Gaussian or something like that. And they're using that to find features. So this has really led to a lot of techniques. And if you don't understand it, most of the computer vision industry didn't understand it for several years either. So, but I want you to get out of it that it gets you these high-dimensional vectors, which are then really useful. We just need to find the nearest neighbors really quickly. Okay. So any questions on this? Okay, so we can now assume that we have this very large set P, which is going to be a subset of some D, and D is big, you know, like 128, right? It could be bigger than this. You can create all these sort of features. I've seen one line of work where it wasn't just 128 features, but there was they took a bunch of these techniques and just glued them all together. So I had like these 1,000-dimensional features, and this worked a little bit better. Right? And you also, because you did this for a lot of images, then the size, the number of images is also big, is equal to something like 1 million. Okay? Okay, but before we talk about this, let's talk about the simpler problem first of just, say, D equals 1, right? So we'll talk with D equals 1, then we'll go to when they're 2 and 3, and we'll kind of build this on up, right? So with D equals 1, the goal, again, is to pre-process this data set so you can quickly find these nearest neighbors. And with D equals 1, what you do is you just, you want to sort P, because it's now just one-dimensional, and then build a binary tree. And I know we talked about this before, but we'll build on top of this a bit. And you know, so you have like, think of, it's hard to draw straight lines here. Okay, so you have this. You can think of having these sorted in some array here. Okay, and so then you build up this binary tree on top here, and okay, and then on search you want to find some value Q, and because these are sorted, then Q is some point here, and you go down binary tree based on Q, and one of the nearest neighbors is one of these 2 points. Right, so pretty simple. This is basically the thing to do in one dimension, unless your data is really big. Does anyone know what to do if the data itself is not just 1 million, but is like you know, a few billion or something, and so it doesn't fit in the memory of your computer, or you don't want to store it in the memory all the time because you're doing some other stuff. So you want to store this on disk. What would you do instead of just a regular binary tree?
Like lazy load subtrees.
Lazy load subtrees, yeah, but the problem is going to be you're going to, every time you need to get something from disk, is every time you do one of these steps down here. And going to disk takes something like 1,000 times as long or longer than getting something from memory. So you don't just want to store this with pointers, right? If you were to build this, you know, you may build a binary tree with pointers so you can easily keep it balanced and updated and so forth. And so every pointer call could be a new block in memory someplace. And so you need to go to disk again. So you may not, that's along the right way, but it's not necessarily the right solution for really big data sets. So has anyone heard of a Btree? So if n is really big, I mean really big, like like maybe like 100 billion, or or is larger, then what you're going to do is this doesn't fit in memory, so you'll kind of break it into chunks which do fit into memory. Okay, so it'll probably be stored in some way like this, and so what you are going to use is what's called a Btree. And so the key part is the hierarchy here, right? So these are stored in memory, but what you do is you make sure that each part of the hierarchy, like here, is in one block in memory as well. So this is also all in one block. So if you take the advanced database classes with Feifei, I think you actually have to build one of these Btrees. Has anyone taken that class yet? Yeah. So did you have to build a Btree or something like that?
Yeah, it's fun.
Okay. Yeah. yeah. So that's but you find that you can really get huge improvements in speed using the Btree. Yeah. So each of these is a full block, and then there's so you want to limit the number of calls to disk. And so this is called a Btree, or maybe there's something called a B+ tree, where so the difference of the B+ tree, in the Btree you actually store some data elements on the nodes. In the B+ tree, I think they're all at the bottom, but they're basically the same thing conceptually. Okay, so keep in mind, very large data use a Btree instead. Okay, but this only works in d equals 1. And if I have d equals 2, I can draw a picture now. My data points look like this. I can no longer just build one of these Btrees. So now the problem becomes kind of an interesting geometry problem. I want to find the nearest neighbor from some query point. So I have some query point, Q. Which one is the nearest neighbor? Is it this point, or this point? Well, maybe the difference doesn't matter so much. We'll get to that. But the kind of in here, the nearest neighbor was just a set of points, and it's either the one on the left or the one on the right. It was pretty simple. In 2 dimensions and higher, what you build is what you can build is some structure called the Voronoi diagram. Okay, so that looks kind of like this. And so the idea is I'm dividing the space up here into these cells So now if I'm inside of this cell over here, and the cells may go off to infinity, and that's okay. But if this Q point is now inside the cell associated with this point, so I know it's closest. If it's inside of the cell associated with this point, then this point is the closest object. This tells me mapping from, it's actually defining. So it's defining the map from RD to phi, to this closest point, right? It's define the map from any point in RD to whichever is the closest point in the set. So if you want to answer the exact nearest neighbor problem, it's essentially equivalent to understanding this Voronoi diagram. If you want to be able to resolve which point is closer, you need to understand this intersection region here. Okay, so it turns out in 2 dimensions, there's this cool fact that the size of this Voronoi diagram, meaning I can draw all these blue lines here and all these intersection points, and and if I have endpoints, the size is O of n. It's roughly the same size as the point set. So that includes the number of vertices I have, the number of edges. I can store the whole structure. Okay, and I can actually build something called, or you can build a searching structure on top of this, where what you do is you actually divide this up into these trapezoids, and you can kind of build some two-level hierarchy over it, and you can search. You can find the nearest neighbor. You can find phi q in O of log n time in R2 by building this Voronoi diagram, then building some structure on top of it. So that's the same time as searching in one dimension. Yeah.
What's the build time like for building?
So the randomized build time is you can do it in n log n. Basically, what you do is you kind of randomize the order of the points, and then you add them in and figure out the nearest neighbor and update the structure. And if you do it in a random order, in expectation, the update to the structure is really small. There are ways you can. So that's the bit. I don't think there's a deterministic way of. There might be a deterministic way of doing n log n as well, but the randomized way is to do it. So you can do it in n log n time too. The space is linear, n log n build time, which you have to essentially sort the points anyway. So it's same as in 1D, and log n query time, right? So if you care about asymptotics, then this is kind of the right way to do it. Okay, so let's say I want to do this in higher dimensions, right? What is the size of this in RD? How big is this? How big can this get? Does anyone have a guess? Without, yeah. N times the number of dimensions. So size of n times d. If it was this, it'd be pretty good. Just storing the point set takes this much space, right? Because every point has d coordinates. So doing this would be great. If this is what you could do, actually, searching in high dimensions would actually be a lot easier, because you could build this and then you could use this structure to look stuff up. The problem is it's actually much bigger. The size is going to be n to the floor of d over 2. Okay? So when d is equal to 2, no, this should be the ceiling. Sorry about that. Okay. So it's the ceiling of d over 2. So for d equals 2, then this is O of n, right? But for d equals 3, this is n squared. For d equals 4, it's still n squared. D equals 5 is n to the third. Right? If I'm building something in n squared time, I can do a lot of stuff. I can check the distance between every pair of points, right? It becomes much harder to actually work with this. There's some cases where you can kind of maybe build an approximate version of this that works well up to d. Maybe you can extend these techniques up to d in the range of 3, 4, and 5. And there's some work on trying to extend it to these cases. 3 is really important if you're dealing with stuff in graphics or something that has correlation to what's going on in the world, because our world is 3 dimensions. So people have looked at a lot of cases for doing meshing and so forth, and sometimes you add time to that and you get to 4 dimensions. So people have looked at these sort of settings, but they're really hard to work with beyond 2D. So we need a different solution here, right? Okay, so for D for medium dimensions, D equals, say, in the range of 3 to, say, 12, roughly in this range. Then we're going to do some different sort of approaches. Okay, so the first, there are going to be some structures that can solve the problem exactly. But this is kind of the point where it's worth looking at the approximate nearest neighbor problem. Okay, so the goal now is to return some some P in P such that so this is given a query point. Such that the distance from our query to P is going to be less than the distance from the query point to the optimal point. This should be a Q. Times 1 plus epsilon. Okay, so let's break this down. So this is the best possible point, and so this epsilon here, you're going to have epsilon in say often 0 to some small number. Often maybe this is 1, you get a 2 approximation. If it's 0.1, you get a 10% approximation. So it's within some. This is some error parameter. So I'm saying, I'm going to set some error parameter. If I set this epsilon equals to 1, then I get a 2 approximation. So that means I'm going to find some point, and I don't care which point it is, some point which is not too much further than the closest point. Right? So why would this be okay? Well, I talked about why we're looking at this nearest neighbor problem at all these applications. Does this approximate nearest neighbor, does this make sense? Oh yeah, that's it. So if someone asks you why, if someone says why, there are 2 great answers. So one is why not, and the other is because. So if it's because, it's because I said so, right? I'm telling you this is nice or beautiful. But why not is, yeah, the approximate distance is probably close enough.
Oh, that's what I was just going to say. There's a lot of error in the data we're looking at. Approximately probably fine for this.
Yeah, right. So the whole one of the points of the last few lectures was that these distances are modeling choices you've made, and to create the data within these these things, you've made some modeling choices of how to create this data. There's noise in there. If you find something that's close to being similar, well then there's no reason to say that the optimal point, the best one, is definitively better than some point you find which is nearly as close. Right? Yeah. So this why not is really because of there's noise in there anyway, right? So and then the because is maybe because this one actually works. This one is easier to do. So I can actually solve this problem a lot easier than I can solve the exact problem. Okay, so let's see. So the basic way of approaching this is, let's create a little bit more space here. Is we're going to think of all of our data points, just for convenience, of lying in some box. Okay, and let's pretend that this box, this is, say, it could be 0, 0 up to 1, 1. We've taken our data and we've scaled it somehow, maybe. I don't know. But it doesn't need to be scaled. It lies inside some box. Okay, and so our data points lie in here. And so this will work in, can think of this in higher dimensions, but I can draw pictures in 2D. So I see some of you are dotting it just like I was. That's in your notes. That's great. So what we want to do is somehow figure out how to look at the space without looking at all of it, right? We're going to do something like a binary tree, but we're going to extend this to higher dimensions, right? And so the simplest way of doing this, and actually the one that gets used most in practice, is called the KD tree. And so the idea is that you're going to kind of divide up the space. So instead of just splitting in the one-dimensional space, well, we're going to split in one-dimensional the space. Basically, we're going to take the point, which is, maybe that was, let's say with this point, and it was the median x coordinate. So the x value, if I sorted all the points in this way and this way, this one is the median, I'm going to divide the points here. Right? So I'm going to call this one P1. And so then I'm going to have a tree, and this point P1 is going to be at the root of the tree. And then, but I need to do this in other dimensions. So now the next thing I'm going to do is I'm going to split each of these halves. Right? But instead of still using the x coordinate, now I'm going to switch to the y coordinate. So this one will now be the median, but only on the points in this half. So I'm going to split now like this. And then maybe this point is the median, and so I'll split like this. So now I have a tree, and maybe we'll call this P2, and this is P3. And so you can think of P2 is on the left, and P3 is on the right. So it's looking just like my binary tree. But now what I've done is I've alternated these dimensions. So basically, it alternates the split dimension every level of the tree. Okay, so let's say I kept doing this all the way down, and so now the next way down was split through here, and you note that the split does not have to be the same point. Here it happened to be, just because my drawing skills are mediocre. But so I split in these different directions at this level, and then I split again through here, and in this way through here, and so forth. And you can conceptually think of, oh, that should have been a different way here. Right, so you keep doing this until there's only one node in every leaf. Right, each cell only has one point in it. And in practice, you probably want to actually stop when there are something like 20 points in the bottom, or some other number, and then do a brute force inside of there. But you know, just like a binary tree, you keep going until there's one point in every cell. Okay, so this is great. Now let's say I've got some point Q, which is my query. How do I now find this, you know, so this is going down as well. Right, so then I have the leaves at the bottom. So I have a query point. How do I find the nearest neighbor? I can use this to find the nearest neighbor too, or the approximate nearest neighbor. How would I do this? Yep. So at this bottom level, I only have 1 point, so I don't need to sort. Right? So
well, first you have to find your point. So you do a descent. You check to see your boxes, see which one you're in. You go to that box. You do an intersection test in the 2 boxes you're inside. You keep descending until you get to the box that your point's in, and then you would look at the elements in that box, and then I guess the box that contains the box that you're in to see what the points are.
Yeah. So let me re-explain this. So that's right. So you start by going Q and you follow down this tree until you find the box that has this point Q. So the query point is in here. Okay, and that turns out it's inside of this cell here. This corresponds with the root, with the leaf node of the tree. And then you find the closest point inside of this cell. Okay, maybe there's 1 point and you just find that. Maybe you store a few points down here. And now you know that if this is the closest point, that, this might not be the overall closest point. We're not done as we were in the binary search setting. But you know it must be within this ball. It must be within this ball. This gives you a lower bound by looking at this point. Okay, so I'm not done, but I've learned something, right? I can now say, let's go back up. Let's go back up to the tree. Now that I have this sense of a ball, I can go and I can check, does this ball intersect this leaf here? Without even checking the points, that's this leaf down here, without even checking any points in here, I know the ball does not intersect this leaf. So I don't need to look down here, right? Then I can go up 1 more level, and that goes me down here. That's this left side here. Yes, this ball intersects, and I can go and check, and well, it didn't intersect this leaf. I had to check these points, and I don't know. It turned out there was no point here that was closer. So this is still my best estimate. So I keep going back up here, and then I need to check the other side here. I don't think my tree aligned with my picture here, but you keep checking the neighbors, and you can prune off whole sections of the tree. At some point, I guess I need to cross over and check here, and maybe I end up finding, say, a closer point here, and I've narrowed down my circle, and then when I try and check this whole side here, which correspond with this half of the tree, I can say this tree cannot have any closer points. So I prune off this whole side of the tree. So you kind of need to go, you walk down to the leaf node, and then you kind of walk back up and you keep refining your lower bound, and hopefully you can prune off whole sections of the tree. You don't have to search. And in practice, this often works pretty well, in this range here. Now, kind of the cool thing is if I'm doing an approximate nearest neighbor instead of the approximate nearest neighbor instead of the exact nearest neighbor, how would this differ?
You could just stop at the first element and then say, this is my error, like I have an error found.
Yeah, okay, so if I found this one, I can say what's the distance from my query point to the next closest cell, and if it's less than, if it satisfies this property, then I can stop. But in practice, what you do, that's kind of what you want to do, but conceptually you'll think instead of drawing, can you see that yellow at all? No? Okay, I'll draw another black dash circle. So you can draw a smaller ball. Okay, and the smaller ball, when you shrink it a little bit, if I did it right, maybe it didn't cross over this blue boundary here. By shrinking a little bit, it tends to help a lot in the printing process. In high dimensions, in these medium dimensions, you're going to be saving a lot because you're cutting off like a fairly big piece of the circle here. I don't need to worry about. And maybe there was a point that was a little bit closer, but it wouldn't have been that much closer. So I can prune this much more efficiently, and this ends up speeding up the process a lot by finding the closest point and then shrinking my lower bound I'd need to find another point within this dashed circle in order for this point not to be a valid point to return. So I end up having to search a lot less of the tree if I shrink my estimate by shrinking the circle a lot every time. For instance, if I found this point and I had this smaller circle, then my estimate here is completely within inside the cell and I can stop. I wouldn't have even needed to go across here. Or go across to this whole part of the tree. So you can save a lot by doing this approximate distance. Okay, so this KD tree works pretty well in this range. I just want to mention in the literature there are kind of there are actually many other variants of this, and I'll talk about some extensions of the KD tree next, actually, which will allow you to go beyond this. But you may see kind of a couple of other common techniques that I just want to mention. There's one's called the quad tree, and the quad tree it splits at every level into it splits into 2 to the d squares. So what it does is every level it picks the center, and so before this was split based on the median. So I guarantee that the height of the tree was always log n, which is great for the KD tree. This says I'm going to split based on the geometry again. So I start by fitting my data in the smallest square possible, and then I always split into 2 to the d smaller squares. And so this by itself kind of, there's a lot of splitting. So your trees are kind of wider now. And maybe that seems good because something about these Btrees were really wide that I talked about earlier. But it becomes helpful when you do these things so where you compress the data. And what you do is that means if you go down someplace and there's only one of the child nodes has points in it, then you kind of like if sometimes you'll split based on the geometry, and basically none of these points will have none of these nodes will have any points. So then what you do is you just connect this node directly to this node. And so this is called compressing the quad tree. And if you do this, you can still get like these results that have like a log n in them in high dimensions. They have bad dependence on D, so they're not often used. But you may see these in the literature, and these are in like 3D. This still works very well. So if you've seen things like the same idea within the quad tree is the same thing that's in like the multipole method, that's in like large scale simulations. It'll be in these well-separated pair decompositions we might talk about later in class, and these spanner techniques. This idea of splitting up geometrically, hierarchically, allows you to do some other nice properties. And then the other technique I'll mention is what's called an R tree. And that's where your points are here, and one node of the tree, your points may be in some way clustered. And so what you do is you guarantee that every level of the tree is a rectangle, but you fit at each node with a small number of rectangles on your points. And it doesn't need to cover the whole area. And so this becomes a node that has 3 children. And so you have to do this thing where you fit a set of small rectangles to this, but there's some fairly good heuristics for doing this. And this kind of is like the compressed quad tree. It compresses your structure as you go instead of having all this empty space in the KD tree.
In our trees, can the rectangles overlap at all?
Yeah, it depends. Sometimes they say no, sometimes they say yes. There are different trade-offs whether you let them overlap or not. Yeah. Yeah, so this is an R tree, and in like the database literature, they like the R tree a lot for 2 and 3 dimensions. So that's another thing that's used. But roughly they all have a similar idea. You still need to to find the nearest neighbor or approximate one. It helps to do it approximately, and you still kind of need to go down and find a good guess, and then kind of go up the tree and prune stuff as you can. And so you still need to use this basic approach. Okay. Okay. What I finally want to do is talk about these very high dimensions. And so we'll come back to class a little bit later. There's a whole field. There's a whole area called dimensionality reduction, where you have some data set which lies in high dimensions, and you kind of take your data set which is in RD, and you go to some, and you project it to another data set in RK. So this is point set. So into another data set. And you want this one to behave similar to this one, but the dimensions to be lower. So we'll talk about this a bit later, but still often this K ends up being, maybe you get somewhere between 20 to maybe, say, 500. So the lower dimension you often need is still pretty big if you do most of these techniques. Sometimes you can kind of force it to be in 2 dimensions or 3 dimensions, and you can do okay, but you tend to occasionally get a lot of error when you're doing this. So these techniques often only get down to still a pretty large number of dimensions. It's more for compressing the data and kind of having a smaller number of dimensions you can actually work with in some way. And for certain cases, 20 to 100 of them is still a very useful quantity. But for searching in near, we still need to work with these high dimensional settings. So we still, and remember, our medium dimensions really only went up to like 12. Okay, and so let me kind of, before I go into explaining how these work, let me kind of explain just one insight into why high dimensions are weird. Okay, and so I'll look at this by comparing 2 things. One is going to be a box. Okay, and I think it's easiest to see if the side length of the box is 2. Okay, so this will be, think of -1 to 1 to D. So this is a D-dimensional cube. Okay, and we'll call this maybe CD. And then we're going to compare this to a ball that just barely fits inside this box. Okay, let's see if I can draw the ball reasonably. Come on, just touch it down there. All right. Okay, so that's. I'm sorry. I'm still learning to draw with this stylus thing. I'm not that much better on the board, but it should look like a circle, and it should just touch all the corners. So this is a ball where the radius of this is 1. So we'll call this BD, which is going to be a ball of radius 1. Okay? And so just to kind of understand what's weird about high dimensions and why a lot of these techniques that we talked on the last slide kind of break down, is let's look at the area, the difference of these areas. Okay, so let's start the volume, okay, in D dimensions, right? So the volume of the cube is easy. It's going to be 2 to the D. So as D grows, this is growing exponentially. Right? Now I could have made the sides 1 and then this volume was 1 and it was fixed, right? But this will be a little bit, it's easier to kind of see it, I think, if you look at side length 2. Now let's look at the volume of this ball in D dimensions. So does anyone know what the volume of a ball in D dimensions is? Turns out that there's not a closed form for it, at least in every dimension. So it's pi to the D over 2 times over the gamma function of D over 2 plus 1. Okay, and if you don't know what the gamma, times the radius to the power D. Okay, so this was, now if you don't know what the gamma function is, kind of if it's an integer, then it maps to, you can map this to D over 2, and we assumed our radius was 1, so I'll drop this. And so if this is an integer, then this, maybe it's an even integer or something, I forget, but it's going to be d over 2 factorial. Okay? So it's not, so this number is still a little mysterious, but what you should see is that as d grows, this value will stay less than 1. And it's actually going to shrink as d grows. But this is basically d over 2 times d over 2 minus 1 times d over 2 minus 3 and so forth. This is pi times pi times pi times pi, right? So this is pi, 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 and this is d over 2 minus 1, and so forth, d over 2 minus 3, or 2. And so what's happening is that at the beginning, at the very left side, when this will eventually be like 1, then pi over 1 is greater than 1. But for each term, you can just multiply these together. This part here in this denominator is growing with d, and the pi term is not. So as d gets bigger, this is shrinking less than 1, whereas this one was growing exponentially. Right? So that means the volume of the cube, as d gets bigger, is much more than the volume of the ball. This is the biggest ball I can fit inside the cube. Okay, so we're talking about the Euclidean distance, and we talked about all these structures back here, right? Now, when you look at the ball and the cube, how do they correspond to each other, right? This ball is like the Euclidean like distance that we're trying to understand, whereas this cube is like the cell in our in the data structure. So this cell in the data structure looks like this box, but we are interested in the ball. And so the volume is much bigger in the box than the ball, so that means if we look at the points inside the box, probably most of them are going to lie in these corners. And very few of them, as d gets bigger, are going to lie within the ball. So we want to estimate the ball with the box in the data structure, and this is not going to work well. So that's kind of why these techniques break down. When you get to maybe 8 dimensions, or really at 12 dimensions, sometimes 20 dimensions, I've heard you can sometimes use these up to, if you're lucky, you can kind of get some of these structures to work, but beyond that, this difference is too big. Okay, so just to, we just have a few minutes left, so let me mention briefly how to do this. There's this library called ANN, which is based on Btrees, which lots of optimizations. And this I've heard people have used it up to d equals 20 successfully, but sometimes it stops working at d equals 6 or 7. You can also use this locality sensitive hashing stuff I've used, but for Euclidean distance, it performs well, but there's some other techniques which perform like slightly better. Roughly maybe the same order of magnitude, but LSH can be more generally Euclidean, but these work best in Euclidean. The idea is based on a KD tree, but you want to do the splits. But when you do the splitting, there are 2 different ways you want to do it. Instead of alternating the dimensions that you split, basically what you want to do is pick some random dimension and split based on that. So pick a random direction, take the median, and split that way. Now you can't just choose one random dimension. What you actually want to do is pick several of them, like 5 or 10, and then you figure out which one has the most variance that you chose and split based on that one. And so then your KD tree is no longer axis aligned, and it works pretty well. The other one is based on a 2 means clustering. And so this will be based on k means clustering, but with k equals 2. We'll talk about that next week. You create a 2 means clustering of your data, and it can be a fairly rough a version of that, and that's what splits your data binarily at each level. It turns out both of these, this two-means clustering will actually create a linear separator the same way as the random dimension split will. And what both of these are doing is they're somehow adjusting the direction you split to the data. So what happens in high dimensions is often your data is space, at least locally, at least within a local neighborhood. And so you can find that lower dimensional space and do the splitting within that. And then it works like the data in the low to the medium dimensions. And then the KD tree works well again. So these kind of simple ideas of randomly, a random direction or doing a two-means clustering to split allow these k-means, the KD tree approach to work up to like several hundred dimensions. The LSH doesn't matter what the dimension is really, except for the runtime it takes to read all the dimensions. But this can work up to usually several hundred dimensions by changing how you do the split a little bit. And these are used like for in the case for the SIF features. They recommend doing the two means clustering as the recommended way of doing it. But all right, so we'll start on next week on clustering, and they'll use a lot of these distances and nearest neighbor stuff as a core tool.
So when you said that it stops working, what does it mean? That like your accuracy or
it means you're better off. It's going to be faster to check the distance to every point.
Oh,
doing
okay.
a linear scan is faster.
Okay.
So it still works, but there's overhead in doing this.
Yeah,
right?
I just wanted to know what does it mean to stop working.
Yeah,
Like, why?
Yeah. It doesn't give you the wrong answer.
Yeah. So I found there is apparently implementation in R, and I think it was developed initially in C++.
Yeah.
But there
they
is an
ported
implementation in R as well.
Okay. Yeah.